Okay, welcome back, guys, to Life at Home Chemistry Shorts. We're going to be jumping into a series on redox reactions, and we're going to go through and we're going to cover the standard method, which is the half reaction method for balancing redox reactions. But before we do that, the first video in this series, we're going to look at how to recognize a redox reaction and how to not just recognize it, but how to know if you actually need to use this half reaction method or not, because you don't always have to use that, even if it is a redox reaction. So let's go ahead and jump into that, and we'll go ahead and get started. Okay, the first reaction we're going to take a look at is the double displacement. And this is a reaction that you may already be familiar with. And so basically what's happening here is you're basically taking some ions or even polyatomic ions, and they're just more or less switching places.
God, you are my mother.
And you're not who you think you are.
Look at me.
I know, we seem to be inside
I'm
each other.
old.
I beg your pardon.
Oh, I'm like the Crypt Keeper.
Okay, that's enough.
And when they switch places, this reaction, we would say this reaction actually happens if you get a precipitate, a solid in the product side. Now, I'm going to assume at this point that you guys already know how to assign oxidation numbers. If you don't, I'll put a link and you can watch the video on assigning oxidation numbers. So I'm going to kind of fast forward through that. A little bit of a spoiler alert here and just go ahead and give you what the oxidation numbers are so we can move through this quicker. And so we can see, sodium is +1, oxygen -2, sulfur +6. And then we have calcium +2, chlorine -1. And then we see the oxidation numbers on the other side. And what we see here is that you actually do not have a redox reaction going on, because you essentially just have some ions that are rearranging to form a precipitate. So in this particular case, you don't even actually have a redox reaction. There's no change in oxidation numbers of your elements going from reactants to products. So there's really nothing to do here except for just balance your equation just like you balance any other equation that you've probably done many times now. Just put a 2 in front of the sodium chloride and it'll all balance out. And you don't have to do anything really special here for this. Now, the next reaction we're going to take a look at is a standard combustion reaction. Now, the basic definition of a combustion is going to be that you're going to have a fuel source that gets oxidized by oxygen. It doesn't always have to be. Typically it's oxygen. And in this case, you would expect it is going to be a redox reaction of some sort. So we can see that hydrogen starts as a +1, carbon -4. Your oxygen, of course, it's in its elemental state, so it's going to be 0 in the reactant side. And then by the time we move to products, you can see that we're starting to change our oxidation numbers for oxygen and carbon. You can see carbon goes from a -4 to a +4, and oxygen goes from a 0 to a -2. Now, in this reaction, though, the question is, can you balance this without resorting to the half reaction method? Okay, now there's a couple of things here that should that'll let us know whether or not we can balance an equation like this without resorting to the half reaction method. So there are two things you have to be able to do when you're balancing a reaction. The first is you have to be able to balance the elements on both sides. And the second one is you have to be able to balance the net charges. A couple of hints that will tell you whether or not this reaction is going to be able to be balanced in the typical way is, first of all, when you're using the half reaction method, it's always going to be something that's in aqueous solution. So if it's not an aqueous solution, that's a pretty good clue that you're not going to use the half reaction method. So let's hop back over and look at this and see if we can balance it the standard way. Okay, so basically all we have to do in this particular case to balance this equation is we just have to put coefficients in front of our oxygen and in front of our water. And if we look on both sides, we have all of our elements, our carbon, hydrogen, and oxygen are all balanced on both sides. And also we there's no charges on the left side. There's no ions that are left to have to balance the charges on. So the net charge on the left side is 0. The net charge on the right side is 0. And I'm going to show you one where they're not 0 here in a minute, so that hopefully that'll become more clear to you. All right, the next reaction we're going to talk about is a synthesis reaction. Now, pretty much in many cases for a synthesis reaction, you're going to be starting with some sort of element, things that are in their elemental form that go and form a compound of some sort. And so almost in every circumstance, your synthesis is going to be a redox reaction. There's going to be a change in the oxidation number. So we know in elemental form, the sodium is going to be an oxidation number of 0, or chlorine is going to be 0. And then when we go to the product, which is sodium chloride, sodium is going to be +1, chlorine is going to be -1. Now, so this is a redox reaction. We can see that sodium has lost an electron, so we would say it is oxidized. And just to kind of learn some terminology here, chlorine would be considered the oxidizing agent because it is the species that took the electron. Now, on the flip side, we see that chlorine gained an electron, so we would say that it is reduced. But since it took the electron from sodium, we would say that sodium is the reducing agent. So that might seem like it could be a little confusing, but that's kind of the way it works. If you have been reduced, then you're the oxidizing agent. If you've been oxidized, then you are the reducing agent. Okay, but as we were talking about with the other reaction that we looked at, we don't have to, if we can balance this without going to the half reaction method, that's always going to be the easiest and simplest way to do that. Now, it is a redox reaction. Now, it's not an aqueous solution. There's not really a charge on either side. So let's see if we can just basically balance this. And we can by just putting a coefficient in front of the sodium and in front of the sodium chloride. So now we can look at this, and all the elements on the reactant side and product side are balanced, and both have a charge of 0, net charge of 0. And so there's really no charge imbalance. So pretty much you can do this fairly straightforward without having to resort to any additional balancing techniques. All right, now let's take a look at a single displacement. And if you guys remember, a single displacement is going to happen when you have a species that's in its elemental form, such as magnesium here, and it more or less swaps out with the silver.
Evening, folks. Mind if I ride along? You might want to scooch over. You did the right thing.
On the reactant side, you've got magnesium as a solid, and then you've got a silver nitrate solution. And then on the product side, you've got silver as a solid and magnesium nitrate as the aqueous, or in the aqueous solution. So I've already balanced this to save a step. And let's take a look at the oxidation numbers to see what's happening here. Okay. Now, if we look at this, we can see that magnesium lost 2 electrons. And so we would say that silver, since it took those electrons, is the oxidizing agent. And of course, silver gained an electron, so it is reduced. And then we would say that magnesium is the reducing agent. So this is pretty straightforward. It's already balanced, so you can tell you can balance this without using the half reaction method. But let's look at this a slightly different way. If you guys remember the concept of spectator ions, ions that don't really participate in the reaction. So if you know anything that's in aqueous solution can be broken apart into its respective ions, and it will be in solution in its respective ions. So it won't be silver nitrate, it'll be silver ions and nitrate ions. And so when we do that on our reactant and product side, we can look for species that don't really go through any sort of change, such as the nitrates. We would call those spectator ions. And if you remember, that's the way we define the term spectator.
That ball is hit really well to left field. And Dahl makes the catch. Or no? Oh, it's gone.
Now, that guy in that last clip was not really what we would consider a spectator, because he actually did participate. However, in a reaction, the spectators do not participate. So you might see this equation come at you slightly different. It may be unbalanced and without the spectator ions. Here, there's no spectator ions. And I've already put in the oxidation numbers for you. We know that we're going to have a redox reaction here. We already know that because the magnesium is losing 2 electrons and the silver is gaining an electron. And we can, if you look at this, it looks like, well, it's balanced as far as the elements go because we have, magnesium, 1 magnesium on each side, 1 silver on each side. However, if we sum up the charges, magnesium is neutral, silver is a +1 charge, and there's only one of them, and we have a +1 sum of charges in our reactants. However, in our products, since magnesium is carries a 2+ charge, then the sum of charges on our product side is +2. So your charges in this equation do not balance. However, in many cases like this, you still do not have to. You could actually balance this using the half reaction method, but it really would not. It would be overcomplicating this. You can simply balance this by just balancing out your charges. And if we take a look, we can do that by just adding a 2 in front of our silvers. And so that'll balance our charges. Now, silver's still +1, but there's 2 of them. So our net charge on our reactant side is +2. Our net charge on our product side is +2. And then, of course, we have 1 magnesium on each side, 2 silvers. And so everything is balanced out. So there's no problem here. This is an aqueous solution, but there's really not going to be an issue here with balancing out the charges and the elements just using the standard balancing techniques that you're already familiar with. Okay, and if you'll notice, when you do balance this out, if you go back to the single displacement reaction that we looked at earlier that has the spectator ions included, if you look, we've pretty much done the same thing with the spectator ions. You got 2 silvers on each side, just like we did without the spectator ions. It's just when you have the spectator ions in there, it kind of forces you to balance it out, without even considering the charges. But then when you take those spectator ions out, you have to make sure that you're also accounting for the charges. Okay, now so far we've really only taken a look at things that you don't have to use the half reaction method for. You can just balance the standard way. And you might be thinking, well, do I even need the half reaction method at all? What's the point? It looks like everything can be balanced the typical way. So we're going to take a look at actually a reaction that will require us to do something a little bit different. So let's hop back over there and take a look at something that we know we're going to have to do a little bit extra to get balanced. Okay, so let's look at a classic redox reaction that you would probably get on a test somewhere or in practice. Let's take a look. Go ahead and do the oxidation numbers here. And we can see oxygen is -2, chromium is +6. And then, of course, oxygen -2, hydrogen +1, nitrogen +3. And then when we go to the other side, we already see our chromium is +3, and then our oxygen stays as -2, but our nitrogen goes to +5. All right, of course, nitrogen goes from a +3 to a +5. So, one of the little quick phrases that we use to remember this is oxidation is loss of electrons. So the nitrogen has been oxidized because it has lost 2 electrons. Now, on the flip side, our chromium goes from a +6 to a +3. So it is actually gaining electrons. And if you recall, reduction is the gain of electrons. So it is being reduced. So in this particular case, though, when you take a look, if you look at the left side, there's some things that really clue you in that you're going to have to do something a little bit different. We're in aqueous solution, and we have a hydrogen on the left side, and we don't have a hydrogen on the right side. So that hydrogen has to come from somewhere. So we really can't even balance out the elements in this reaction without doing something a little bit different. You can't just put coefficients in front of stuff and get this balanced. And and our charges, our net charge on our left side is different than our net charge on our right side. And so, once again, there's going to have to be something a little bit different with this in order to get it balanced properly. And that's where the half reaction method comes in. Okay, guys, that should just about do it for this first video. There are going to be 2 more videos in this series, so I look forward to seeing you back for those other videos as well. Don't forget to like this video and hit the subscribe button, and I will see you guys next time.